I want to focus on what are the challenges for TinyML. We know that TinyML is a composition of embedded systems and machine learning. We'll first look at the challenges from the embedded systems aspect before we transition over to machine learning, because that sets the context, the scope of how we deploy machine learning onto that hardware. So as with any system, an embedded system is like a regular computer. They run software on hardware. However, they are very application specific. They interface with the physical world through sensors, compute controller updates, and output through actuators. Embedded systems are everywhere. These little microcontrollers are used in dedicated applications such as wireless routers, industrial robots, washing machines, parking meters, elevators, and also critical systems such as automotive, avionics, aerospace, and industrial control and automation. For example, today's cars have between 40 to 70 microcontrollers in them, all the way from engine control, infotainment, seat adjustments, and tire pressure monitors to safety critical crash sensing, airbag deployment, and electronic stability control. Hardware is the first area of focus for us. Now, typically, when you take any kind of computing system, the hardware is made up of three fundamental building blocks: the compute, the memory, and the storage. The compute is the brain. It's effectively what you do with all your processing. That's where the processing is done. The memory is where you temporarily store your data. It's like short-term memory. And your storage is like your permanent hard disk. When you power off, it still remembers your data. It's called non-volatile storage. So these are three fundamental building blocks of any computing system. Now, when you put these three things together, there is a difference between what a microcontroller is and what a microprocessor is. If you're watching this video on a laptop or some sort of computer like that, you've got a microprocessor that's doing a lot of heavy lifting. The microprocessor is a much bigger piece of a computing engine versus a microcontroller, the thing that we are talking about, through this course, of which there are over 250 billion of them out in the world. It's a very different computing system as a whole. Let me emphasize these differences to you. When you take a laptop, for instance, there's a small part that's called a microprocessor, but that microprocessor interfaces with a bunch of different discrete components. It's only one part of a bigger puzzle that ties together all these components, and such as your networking, such as your memory, such as your storage. So you have to buy the microprocessor, and then you have to put all those other components and connect them together. And that's how you build a traditional desktop, for instance. The microcontroller, on the other hand, is very different. When you buy a microcontroller, it's already integrated. For instance, the processor, the memory, the storage, they're all tightly coupled and integrated in one monolithic block, one package, one kind of chip die. So big here is, of course, relative. If I kind of to generalize these into critical bullet points, I would say that the microprocessor is the heart of general computing, general purpose computing, versus the microcontroller is at the heart of embedded systems. An embedded system here versus a general computer for microprocessors. A microprocessor is just one part, and it interfaces with external components of memory and storage, versus in the context of the microcontroller, these things are tightly integrated into the system all together in one package. Again, a microprocessor is meant for general purpose systems like laptops, desktops, servers, where you get to configure things. Those interfacing capabilities naturally lend themselves to becoming a bigger system. Microcontrollers are typically designed for fixed functions. Like take, for example, being able to measure your blood pressure with a blood pressure monitor. It does that one task and it does it really well, but it can't do any other task. Like it can't play music, for example, or be able to control an elevator to a particular flow. It's a very specific task. A microcontroller is all about making them tiny because this form factor is small, and so you tend to squeeze things down. Well, here's a complete example of a microcontroller. You've got memory, you've got RAM, and you've got your processor. Everything is fused together inside this one single block that you buy. And it's quite unlike, how you buy parts for a regular desktop where you cherry pick and choose different things. Then you can build them in any configuration that you want. For instance, my laptop has 32 gigabytes of memory, which is something that I custom ordered from Apple. Versus if you buy a stock laptop, it only comes with 8 gigs of memory. So I have this option to configure what kind of system I wanted. But if I'm looking at a microcontroller, then it's all packaged already into one small thing. And that's how I buy a microcontroller, or that configuration of that microcontroller from a family of microcontrollers. That's one fundamental difference, the major difference I want you to keep in mind. So microcontrollers generally tend to be quite preset in their functionality. And often a big embedded system might include a phone, which is a very complex embedded system. That might include a whole bunch of microcontrollers, say for your audio processing, say for your photography, for biometrics, for networking. And they put all together to provide these different functionalities as separate microcontrollers. Now, because of this flexibility, as a microprocessor ends up to being big, in fact, and that's why your laptop is much bigger, because you have to configure the system with discrete components. Now, these are the key difference. And if I was to take a step back, up to like seeing some ballpark numbers in order to what kind of context, we are talking about in terms of big and small. From a computing perspective, if you look at what's called the frequency or the clock rate, how fast the processor can run. If you look at the regular microprocessor, it can run between, say, 1 gigahertz to 4 gigahertz, versus a microcontroller can run between 1 megahertz and 400 megahertz, right? So that's a whole order of difference over there, at least. From a memory standpoint, you can have megabytes to gigabytes of memory for microprocessors, versus you tend to have small, like little kilobytes of memory for a microcontroller. Storage tends to be on the order of gigabytes versus terabytes and terabytes, versus for a microcontroller, that tends to be kilobytes to megabytes, barely. And from a power consumption point of view, it's on the order of tens of watts to 100 watts for a microprocessor, and versus it's a few orders of magnitude much lower in microwatts and milliwatts for the microcontroller. And so this is like a couple of orders of magnitude difference between compute, memory, storage, and power consumption, and so forth. Now, what are the implications of all of this? What does this all have to mean in terms of less amount of memory, less amount of power consumption? Well, that means you got to think about how complicated is the task you're running. If I want to have smart glasses, for instance, if it needs to be extremely high real-time processing, that being able to have the compute capability where everything runs extremely fast, well, the microcontroller may not be a good fit unless we're able to trim down the application processing needs to be small enough. Secondly, it's like, how much memory do I really need? For example, if you're looking at anything between 2 kilobytes to 512 kilobytes, if you understand the task that you want to run, say to process an image or an audio stream, and you understand the requirements in terms of latency and computing needs, then you'll be able to pick the right microcontroller. And the other question is, how long does the job have to perform? Is it something that needs to be constantly run, or is it running intermittently? Well, that has implications in terms of power consumption. We'll go into all of these into a lot more detail as we step through the course.